Hi, my name's Andy Flowers, amateur radio call sign K0SM. Have I got an interesting antique radio restoration project for you today? We're going to take this AM broadcast band ovenized oscillator and we're going to move it up to 160 meters. Now, the first question you might ask is why in the world would I want to take an AM broadcast crystal and move it up to 160 meters? A good friend of mine, Mark Ertl, AE2EA, recently acquired an RCA BTA 250M transmitter. Now, this is a Class C AM broadcast band transmitter that would have been used by relatively low power stations starting in the probably 1950s. And I imagine they sort of fell out of service during the 70s. My guess is when tubes started not being easily available and there were better technologies. Has a long and storied history. It started off in Pennsylvania, ended up in Western New York, and in the hands of a broadcast engineer that used it for field tests. He's got a whole video on this. We'll have a link to it below. I really suggest you go watch it because it'll give you some context for what's going on. What he did is he moved it up to 160 meters. And to do so, he did what most hams will do. He put a variable frequency oscillator where the crystal oscillator used to be. And hams like this because it gives you the ability to operate on multiple frequencies, not just one fixed frequency where you happen to have a crystal. So that's good for modern operation. However, there's something to be said maybe for running it the way it was made. So the ability to have an original crystal to run in the original equipment is something kind of neat. It'd be fun to try that. So this is the crystal that came with it. He dropped this off at my house today. So we're going to take a look at it. We're going to tear it down and figure out what we need to do to get this thing up to 160 meters. Now, the first thing I like to do with a kind of an unknown piece of equipment is just look at the markings, look at how it's built, maybe do a little research on it and see what we can tell from the outside before we go inside and maybe do a little damage. So just looking at the label on this, there's a really good clues about what we're going to find inside. Probably the most interesting one here is the date code, 75.5. So I assume that means that this was May of 1975. Now this is important because we have to think about what crystal technology was like in 1975 versus, for example, 1950 or even the late 40s when these oscillators were first being made. Chances are when we get in here, we're not going to find just a bare sort of free-floating crystal oscillator, an air gap crystal oscillator. I'm willing to bet that we're going to find a smaller crystal, probably like an FT243 or an HC6, something in a can would be very likely for 1975. We're going to find out when we get in there. All right. Well, here's our moment of truth. I've loosened these screws. Let's see what we got. Look at that. I was right. There's a metal can in there. All right, and this is interesting. Here's the top of the bimetallic strip, the little thermistor that's there, that little thermostat control. It looks like they've got it kind of in its own little cavity there. Those two cavities aren't connected. But that's a big hunk of metal and actually not a very big crystal. It might surprise you because if you watch the video of this transmitter, the oscillator is an 807, which is a pretty big tube. And here it is running with a little HC6. Now, if you actually go look at the schematic, there's only 250 volts on the plate of that tube. So this thing isn't running too hard. Yep, that's an HC6, or it goes by a bunch of other names. We usually call these HC6s. It's a plug-in large can crystal. Yep, it is same as what's marked on the outside, 1.140. So 1140 is what this thing was set for. So there you go. And if we look inside, yep, there's our socket. All right, so we're going to have to figure out what to do here because one of the problems I'm going to have is it's hard to grind a crystal or find a crystal for the frequency that you're interested in this style. So I'm thinking that maybe we can change that socket out and get something a little more ham friendly. So I'm going to take a look around, see what I can come up with, and I'll get back to you. I've given it some thought, had a little look around, and made some measurements here. And I've got a plan of attack. Well, I don't know that this is going to work, but we'll give it a go. So what I have here is another HC6 socket. So I haven't taken the one out of here yet, but these are basically identical. And you can see how this works. It just plugs in here. If you've never seen one of these before, that's all it does. Now, one of the things I notice is this cavity is actually a whole lot bigger than this crystal. There's a lot of headroom in there. And I'm thinking that maybe this is Rev 2. I'm actually thinking that originally there was an earlier version of this that might have taken a crystal that looks like this. This is, you guys, a lot of you will recognize this. This is what we call an FT243. These were used in all kinds of military equipment in World War II, Korea, but early novice era hams loved these things. The novices had to be crystal controlled, so you got your precious crystal in the ham band, and this is where your transmitter went. This is one that happens to be for 160 meters. May not be the frequency Mark wants to put it on, but we'll cross that bridge when we come to it. What I noticed is that with a socket down in the bottom, looks like there's going to be enough headroom for this. I actually think this may have been designed originally with the idea of an FT243 in there. It's just the right size. Don't know if that's true or not. But what I'm going to try to do, at least make a valiant attempt to, is to take this socket. Here's an FT243 socket. And I'm just going to unscrew the one that's there. Okay, well, that ended up being a little bit harder than I thought it was going to be. I ran into a problem where the height of the new socket was just a little bit too much. So I actually had to sand it down and just lower the height of the socket just enough so that our crystal would fit in there. And there it is. And the lid does sit flush now, which is good because that should help. As long as that sits down tight, we'll be able to maintain temperature in there with the thermostat. I also ran into a problem where the Erie was a little stingy on the lead length here, so I had to actually make some extensions. I've hidden it pretty well. I've gotten a little plastic boots back over the pins of the socket, so you can't really see that. I checked it out, and it oscillates fine, so I didn't short anything out to the case or anything like that. It's a little tight in there. So I think we're going to be good to go with this. Now the challenge is going to be, how are we going to get a crystal on the right frequency? And that's now, if you're familiar with these FT243 type crystals, usually what you find in here is a little sandwich. Looks like this right here. This was taken out of a much higher frequency crystal, and it's all it is there's a spring in there that presses these two electrodes together around a very thin piece of quartz. There it is, very, very thin. Right. So we call that a pressure mount, right? Because there's actually pressure being put on the crystal blank, and it's just kind of held in place there. And they did that, because this thing had to go in a tank radio or something like that, where it'd be all shit, vibrating around and things like that. That's pretty typical. So when you hear about people grinding crystals, that's the kind of thing that they're used to seeing. Now this one's down at 160 meters, and a lot of times down there you actually find a different construction. So we're gonna pull that out. This is the same. There's a spring there that's kind of pushing down on something, and a neoprene gasket just to kind of try to keep water out. Although after 75 years, we'll see. There's a little insulator here that just keeps the spring from touching the top electrode underneath here. And we'll go ahead and pop that up. All right, so there's the insulator. It's just a little piece of fiberboard. There's one of the contact plates that goes to this pin here. I'm just going to lift this up. So far, this is the same as you would find in any other. And then you get this kind of funny shaped electrode. I'm going to bend that way back so you can see. All right. So there it is. So far, it kind of looks the same. Now I'm going to pop this out very carefully and see if I can do it. I got it. All right, one of the glass beads fell out. This is actually an air gap holder. All right, the way this works is there's a little glass bead there. I'll set this down. Here's the top electrode. right? And what it does is it actually there are three glass beads that sit on these tabs that you see here. I'll try to move this one back on. I can't get it. But it actually sits on top of those glass beads and doesn't actually touch the crystal. The crystal's actually kind of floating in there. There's a little tiny air gap, usually between about 0.5 mils and 0.3 mils. That's usually what they shoot for here. And so that there isn't actually physical contact between one of the electrodes and the piece of quartz. Right? They did this because this made for a higher Q crystal, and because low frequency crystals have a real tendency to have a high ESR. It's just part of the physical properties of the quartz. The air gap was a way to kind of get the crystal activity, what we would say crystal activity, back up by not trying to sandwich the piece of quartz physically. So if you're going to work on one of these, watch out. You want to save those glass beads, because if you don't have those, it's not going to work too well, because you're going to be squeezing the quartz with two flat plates, and you don't want to do that. So I talked to Mark, and he would like a crystal for 1,940 kilohertz. Now this is for the Antique Wireless Association AMnet that meets on 160 meters right now on Monday nights. And so to do that, I've got to move a crystal for him to get there. The closest thing I could find in my stash was, in fact, the 1870 kilohertz crystal that I showed you just a moment ago. So let's talk about how we're going to do this. Now, most crystals that operate in the megahertz range vibrate in what they call a thickness shear mode. Now, the best analogy that I can use for this is if you imagine a piece of Jello sitting on a plate. I take the plate and I shake it side to side. Well, what's that going to look like? Well, that Jello is going to kind of shift one way and shift another. It's going to do this kind of thing, right? So the frequency at which this happens is going to be dependent on the thickness of the Jello. So I have our little crystal here, and I've got it in a good old-fashioned micrometer gauge. I can pretend this is the 1930s. I'm going to do some crystal work. All right. I don't know if you guys can see that too well. Let's see. Yeah, it's all right. So that first mark is 25 thousandths of an inch, and we're up on the 10th. We're about 35 thousandths of an inch. Now, I happen to know that this crystal oscillates at 1,870 kilohertz. So that means that I can figure out well, I can go to a formula actually, and it'll tell me the rate, if it's this thick at this frequency, I know what axis this crystal was cut at. There are several common ones. This one happens to be what they call an AT cut. It would be kind of what we would expect for this frequency range. By my calculations, we've got to take off about 1,000th of an inch, a little bit more. Now, I could do this by measuring in a micrometer. What I'm actually going to do is grind it down physically using some carborundum, and that's what, and check it periodically as I get close to frequency. And that's what this plate is here. I've just got plate glass glued down to a piece of wood. It's a very flat piece of wood. And I've got 3 plates here, and that's just for different grits of carborundum. If you want to move it fast, you want maybe a 400 grit. Not sure I'd go any lower than that. And then you can move to a 600 or 800, and then you want to finish off with something like 1,000 or 1,200. That really gives you the best finish on the crystal. I'm going to go a step further, and I'm actually going to etch it to frequency. That's really sort of the gold standard. That involves chemicals. I'm probably not going to show you a whole lot about that. It's not a real safe thing to do. So I don't really advocate that. This is kind of a special case. We're trying to make a quality apparatus that isn't going to age on us. We'll see how well we do. So that's what we've got going on here. We're going to free up this crystal. All that's involved is, putting some carborundum powder down. I like to use a mixture of Dawn and distilled water. Kerosene can be used if I'm inside. I don't really like to use stuff like that. Alcohol can be used as well. That'll work. Anything like that. But even though I'm only moving this thing about, 30, 40, 70 kilohertz. This is the equivalent of, if you've done a 7 megahertz crystal, this would be like moving it from about 6,400 into the 40-meter band. This is actually a lot of material that needs to be removed. Just because to change frequency, you need to remove a whole lot more quartz down at 2 megahertz. So we're going to get started. It's probably going to take me a very long while, but hopefully we'll be successful. Okay, we're back, and I finished up grinding this, at least as far as I'm going to go. So let's just kind of see where we are here. So just so you know what I did here is I finished grinding. I got this thing to about 1941 kilohertz. In fact, it was right on this counter. And then I put it in for 20 minutes in the ultrasonic cleaner at about 45 degrees C, I think. One of the things you'll notice, we'll see if we can get this come up. All right. So it went up about 300 hertz just from the ultrasonic cleaning and drying it out. There's a lesson in here. Just after you grind a crystal, no matter how clean you try to get it, there's going to be material left on there. You really need to scrub these things down. I like the ultrasonic cleaner. It does a real good job of getting things you couldn't possibly get on the edges, especially with a thick crystal like this. However, if I were to have done this at, say, 7 megahertz, that 300 hertz is going to be multiplied probably times about 4. So that's like that's a fairly significant change. So if you're actually trying to move a crystal by grinding, there's likely to be a significant amount of aging and things like that if you don't get things completely clean. So we're ready to etch this thing. We've got about a little less than 4 kilohertz to go. My guess is at this frequency, with the weak solution that I'm going to be using, that's going to take the better part of the day to move that far. But we just got to be patient and check it fairly often, make sure we don't go over, and hopefully we'll get it there. Okay, so I brought in the crystal oscillator, and now we're running both the oven and the crystal inside the oven, and we're measuring frequency as this thing heats up. In fact, I've been running this for about half an hour. So we should be approaching the equilibrium temperature of 75 degrees C inside the oven. And it's getting toasty, so that's a good sign. Let me explain the setup here. We have a WR50B signal generator, and this has a crystal port on it, so you can actually use it as a crystal oscillator as well. I take the output of that, and I'm running that into a HP5350B counter. And this has GPS lock on it back behind the table. So this is going to be about as accurate as we can get here in a home lab. And you'll notice that it's pretty much stabilized out at about 30 hertz below our target frequency. Now that's actually really good for a couple reasons. The first is that the oscillator itself in the BTA250M has a trim pod in it. So you didn't actually design the crystal to be exactly on. What you did is you put the crystal in, it gave you the stability, and then you moved a trimmer to get within the plus or minus 10 hertz that the FCC required back in the 50s and 60s. So as you see, this thing's pretty much stabilized out, and you can see the current going on and off as the heater is now pretty much regulating that piece of metal at this point. So this is probably where I'm going to leave it. The other reason it's good to be a little bit low is no matter how good a job I do of grinding that crystal, I still ground a crystal, and this thing probably will age upward in frequency, assuming I got everything really, really clean. And I think I did a decent job of that. We'll find out over the years. Maybe Mark can tell me in a decade, and we'll see how close its transmitter is to frequency. So I think I'm going to wrap this one up and give it over to Mark and see if he can get it to work.
So I've got the transmitter fired up, and I thought I'd give Andy a shout. I tipped him off that I'd be calling him, so he's listening for me now. That'll give him a chance to hear the fruits of his labors. So here we go. Kilo Zero Sugar Mike, Kilo Zero Sugar Mike. This is Alpha Echo 2 Echo Andy. How do I sound, Andy?
AQEA from K0 Sugar Mike. Sounds really good, Mark. Yeah, you're easily S9. We're not too far away, but you're running a whole lot more power than I am. Go ahead, Mark.
I'm thinking, Andy, you probably hardly need a radio. Maybe a crystal set would work on your end if it could tune up into the 160 meter band. But yeah, the thunderstorm just passed, and I got blue skies down here now. Although part of what you said was wiped out by some lightning someplace, who knows where. But surprisingly, your 2 watts is doing pretty good. So power is good, but you don't necessarily need it.
Yeah, thanks, Mark. Yeah, you're actually only my second contact here on the Central Electronics radio. I had this on for the AWA net a long time ago, and I think it was in July, and somebody was just barely able to make me out all the way over in Vermont, which really isn't too bad for a July.
If you enjoyed this video, consider becoming a member of the Antique Wireless Association. Just follow this link to the AWA website to learn more, and thank you.